So yeah, we will be starting our 40th lecture on power system operation and control. Here in this lecture we'll be focusing on control of reactive power. So the main focus is in this lecture is going to be control of reactive power. So we have already completed the active power part, and we have already solved one numerical in the last class. I hope everything is clear in this numerical. Any queries on this? So this numerical is given in the book. I have already shared the link as well as so you can easily quickly see there. And just a point to remember that in that book they are taking the frequency as 60 hertz because the book is written in US, so that's why it's 60 hertz. In all of our examples, I have taken the frequency as 50 hertz because obviously we are in India, so India has a 50 hertz frequency. Okay, so you can just see that. Okay, maybe if some answers are different, you can just change the frequency and get the same answer. Okay, any queries so far? Also, regarding the term paper, I'll be discussing at the end. Just remind me once. I just wanted to ask if everybody has completed the term paper or not, because I think today was the deadline. Okay, anyways, so let us start. Am I audible to everyone? Okay, good. So basically we saw in AGC that the idea is like this. So basically if the load increases, the primary frequency control or primary load frequency control will stabilize the frequency. It will stop the frequency from further dropping, and then AGC will pump the generator to bring the frequency back to the 50 hertz value. And this part, the second part, is actually the AGC. You can also call it as AGC, you can also call it as supplementary control, you can also call it as secondary load frequency control. So this we have seen, and once the frequency stabilizes, then we go for the third part, which is economic dispatch, OPF. All these things come after this, after the third part. So obviously we will focus on economics once everything is at stable state, right? So that is always there. But what people say that we should also, while in the second stage, which is nothing but the secondary load frequency control or AGC, here we also want to bring the frequency back to the 50 hertz. In this process, we want the generators or the economical generators to be used. We do not want more diesel and gas generators to be used, because if you use more those type of generators, then obviously at the end customers has to pay that price for bringing the frequency back to 50 hertz. So therefore we have already seen the concepts of participation factor, and what we can do is based on these participation factor, when we are requesting the generator to generate more to bring the frequency back to 50 hertz, and so here we use the concepts of participation factor, which we have already seen before. So you can just impose this participation factor, which is nothing but the double derivative of the cost function, and whatever is the delta load change has taken place, because of which the frequency has gone down. You know, based on the participation factor, which generator will be cheaper to provide that extra generation, and based on that you can easily calculate the generators which will be which will participate in the terms of economics for bringing the frequency to 50 hertz, right? So this we have already seen before. Now the how to implement AGC. So just wanted to give you a quick idea that it is actually every information is telemetered. Telemetered means it is being communicated to the system operator. All the information of the P set point, voltage set point at the generator terminal, because obviously P and V are continuously changing, because you saw that if the frequency changes, the generator also changes its generation. So that information also has to be communicated to the system operator. If we do not communicate, then obviously we will not know how much each generator has to change to bring the frequency back to 50 Hz. Also, you need to get the information about ACE. ACE is area control error. This information is also required. Here filtering is added because there can be some noise, because area control error is the net change with all the tie lines connected with the area. So there can be, let's say, one area is in the center and let's say 5 areas are connected to that. So you have to take the net error for all the areas. So that's why filtering is required. You also need to observe the rate limits. What is the rate limits? Rate limits is nothing but the line limits or the voltage limits at the terminals. You also need to ensure that this ACE must be brought equal to 0, or the area control error must be brought equal to 0 within 10 minutes of the disturbance. So this is the regulation what is imposed, that we have to ensure that area control error should be less than, should be made 0 within 10 minutes. Also, AGC and ACE, the process of AGC is executed between 2 to 4 seconds. This information what I am giving you, this is of US, but in India, as I told you before, this AGC is not there in India so far. So this is the secondary control. India has the primary control. Obviously droop characteristic is there, but secondary control is not there in India. So in India, the idea of bringing frequency is based on uninterrupted frequency change. So I'm not going to that. That is a bit of a confusing thing. So let's say in x-axis, I'll just quickly give you a brief idea. If let's say in x-axis frequency is there, y-axis power is there. So let's say frequency is increasing. So basically you have to reduce the loads by this much value wherever this is intersecting, and in and if let's say if frequency is if the reverse will be there for the generators. Let me just draw it for, so the reverse will be for the generator. If let's say frequency is increasing, the generation has to reduce at this value, or frequency is reducing, the generation has to increase at this value. And this slope, this concept is actually used in India for bringing the frequency back to 50 Hz. And this slope is decided based on, the slope is giving you a price signal. So the slope or the angle of this slope is a price based on which this change is decided. So whatever is the slope, and the slope is being continuously adjusted by the system operator based on the regulator's permission, and based on this change they keep on bringing the frequency to 50 Hz. So this is the very simple way by which they do it, but it is not obviously not based on the scientific logic, which is AGC. So AGC and ACE are the concepts of US markets or US systems, not in India. It is still not there, but soon it will be there. People are implementing or started testing AGC on pilot basis at some locations in India. Also, if you have to implement AGC, you have to fix the frequency bias setting, that B1, B2, what we were discussing. Also, AGC has to be, we have to check for AGC based on its performance. The idea is to ensure that minimize the fuel cost, minimize the wear and tear, and minimize the undesirable range. So this we have to ensure. Also, we have to check for emergency mode of operation. So let's say if AGC is also unable to bring the frequency back to nominal value, then you need to execute emergency mode of operation. So this also you need to ensure. And lastly, you have to check for the speed governor dead bands. So that will also affect the performance of AGC. So this is the quick understanding how AGC is implemented. So with this we have completed the control of active power part. Now I'm going to start the reactive power part. Is there any query so far? Okay, if no queries, then let me start the reactive power and voltage control. So this topic is going to take around 45 minutes for me to complete. So let's just bear with me. It is just a story because there is no numerical on this. It is just a story. You can listen and you can easily understand everything. And obviously I'll be sharing this video with you so you can easily rewatch it again so that you can easily understand it. So basic idea is of reactive power is basically we want to control the voltage. And why do we want to control the voltage? The basic criteria is that voltage should remain within acceptable limits. And why do we want it? Because if you violate this acceptable limits, the equipment or the appliances, they can only operate within a specified voltage range. If you violate that, then their life or the inside of that may get damaged. So therefore we always want to ensure that voltage is within the acceptable limits. We also discussed that voltage affects in brownout. If you remember that if voltage reduces, then more current is drawn from the network, and as you draw more current, then further voltage drop happens, and this iteration keeps on happening, which eventually may lead to instability in the system. So therefore system stability is enhanced when you keep the voltage within a specified limit. And also if you, let's say, if voltage is not within the limit, or it is the range of voltage difference or delta V is very high, means delta V means the voltage between two terminals, then the current flowing within that terminal will be high, eventually the losses will be high. And specifically if more reactive power loss or reactive power flow is happening on a line, we are not using the line efficiently, because we want more real power to flow on a line instead of reactive power to flow on the line, because obviously real power is the actual power what we use. Reactive power is just supplementary. So if you do not maintain the proper voltage, then more reactive power will flow, and eventually you will not be able to use the transmission line efficiently for your real power purposes, and eventually it will lead to congestion, and you know the OPF and everything, how the congestion will treat the system. The prices will differ, and lot of things can happen. So that's why this is not recommended. So these three are the main reasons we want the voltage to be within the acceptable limits, right? And now problem in the voltage is basically obviously system is huge, and frequency was very easy. Frequency, because let's say if the frequency you measure in towards south of the India, or the north of India, or the center of India, or east or west, anywhere within a network, the frequency is going to be same. It is a synchronized thing, so it all across the network the frequency is always going to same. So that is a very uniform thing, and a global phenomena type of thing, where you get the single frequency across the network. But problem happens with the voltage is that it is not single. Voltage is a local phenomena, and voltage will be different at your home, at my home, at north of India or south of India. Everywhere voltage will be different, and there are lot of components which provide voltage support. Real power only generators can provide, or batteries or renewables, they can only provide real power. But reactive power, there are a lot of components in the system which actually consume or produce reactive power. So therefore it is even more complicated to balance or to ensure that the reactive power or the voltage remain within the acceptable limits. And whenever I talk voltage or reactive power, both I'm using analogously, because voltage is actually majorly depends on the reactive power. Or we cannot generalize it, it also depends on real power, but as you know from the transmission system point of view, because we have a high X by R ratio, you can say easily say that reactive power is mostly affects the voltage, right? So now can you tell me what all components which produce and absorb reactive power? Just 2-3 examples in the network. Yes, and more. Yes, fact devices. Yes, nonlinear components also. Also, I can just quickly tell you here that synchronous generators, they can provide reactive power, they can produce as well as absorb. Even transmission lines, they produce and absorb reactive power. Underground cables, transformers, loads, obviously as you have mentioned, nonlinear loads, linear loads, all the type of loads generally absorbs reactive power. And there are compensating devices which are basically shunt reactors, fact devices. These compensating devices, they also can help in producing and absorbing reactive power. So let us see some of them very quickly and try to understand their basic fundamental idea here. So if you broadly see, there are 3 broad categories which actually helps in voltage control. One is AVR. AVR is automatic voltage control, with voltage regulator, which is there in the generators. So synchronous generators, they can change their excitation, and they can change their field current, and they can eventually change the voltage at their terminals, and then they can, due to their change in voltage, eventually the system voltage will get affected and may improve based on the change in the generator voltage. Another devices are shunt capacitors. Shunt capacitors, reactors, synchronous condensers, SVC. SVC is the static var compensators. I'll come to that later on. Line reactance compensators, series capacitors, regulating transformer, tap changing or boosters can be there, which also affects the transformer, which also affects the voltage control. And lastly, you have passive and active compensation. It is mostly other categorization is passive and active compensation. Passive means like shunt capacitor and shunt reactors. If you can just keep it connected with the network, then you say it is a passive compensation because you are not changing the shunt capacitor or reactor. If I say that it is active compensation, that means you can vary the capacitors, vary the reactor. So basically switched capacitors, switched reactors, or synchronous condensers. Specifically SVC comes under the active compensation, because they can easily change their voltage set points very quickly to support the voltage across the system. So there are broadly 2 type of compensation. One is passive, which is fixed or not varying. So for example, the line reactance compensator, series capacitor, they are generally fixed. When we talk about fact devices, they are basically active compensation. They can easily change their reactor voltage control. Right. So these are the 2 broad categorization how we can divide the voltage control. Let us see some of the components now. So basically, let's say if we talk about shunt reactors, generally shunt reactors, they are used to reduce the voltage. Basically, if you have a situation of over voltage, then you can apply a reactor there to reduce the voltage, and this generally happens when you have a overhead line which is more than 200 kilometer of length. So that means there may be an issue of Ferranti effect. So basically it's a long transmission line, and whenever this long transmission line is there and if it is lightly loaded, you know that it will have a possibility of Ferranti effect is there, and Ferranti effect means the voltage at the receiving end is higher than the voltage at the sending end. And if that happens, you generally apply shunt reactors at the receiving end so that the voltage can be brought down. And for the shorter lines, you used switched reactors because there could be a situation where under voltage can be there, so you can switch off the reactor and the voltage can be brought back to the normal, right? Now let's talk about shunt capacitors. Shunt capacitors, again, it is used to improve the voltage. Wherever it is connected, it will push the voltage up. The advantage is that it's a low cost, it is very flexible, easy to install and operate. Only disadvantage that it provides reactive power in the proportion of voltage square. So that is the only, we can't say it is a disadvantage, it is like a fixed thing. So you cannot, means basically whatever is the voltage appearing on its terminal, it will provide the reactive power in the proportion of that voltage, and as soon as it provides reactive power, the voltage at that terminal will improve a bit. So that's why we say it's disadvantage, because it is fixed. You cannot change the reactive power what you can provide from here, right? So if you say in terms of distribution system, it is mostly used for power factor correction. If we talk in terms of transmission system, it is used to improve or reduce the reactive power losses and improve the voltage profile. Now let us talk about series capacitors. So again, series capacitor, the idea is same. You can, wherever the series capacitor is there, it is connected between two terminals, or it is connected in series with the transmission line. So let's say if the reactive power or the voltage is dropping, if it's a long transmission line, so you can add a series capacitor and it will improve the voltage at the receiving end, and it actually supports in reducing the reactive power losses. It increases the power transfer across the transmission line, so that is also a useful feature. So basically you do not have to transfer more reactive power from the sending end. Instead of that, the line is generating more reactive power. So from the distribution system point of view, it supports in reducing, means it improves the voltage profile or reduces the voltage drop. It reduces the instantaneous change in load current also, because series capacitor actually does not allow this is the basic fundamental phenomena of capacitors. I hope you all remember it, that it does not allow the load current to change instantaneously. It actually gradually changes the load current. And in terms of transmission system, voltage is improved, voltage profile is improved because of more reactive current. It also can help in bypassing and reinsertion. So what you can do here is basically you can switch off the capacitors which can bypass the power flow from the other areas, and then again you can switch on the capacitor, series capacitor, which can actually bring the power through this transmission line. So that feature is also there in series capacitors. Also, wherever this location is important for the series capacitor, wherever it is placed, it only affects the voltage of that area. So that's the advantage of voltage. This locational advantage is also, feature is also there for the shunt capacitor also, because obviously it gets affected to the neighboring areas only. Any queries so far? If not, then let us see the synchronous condenser. So synchronous condenser is basically a generator, but a generator which does not where prime mover is not moving or the rotor is not moving, it is standstill, and there is no mechanical load connected to the rotor. You just basically just from the excitation system, you excite the generator, and whatever voltage you are getting, based on that, you based on the standstill rotor, you can do give the excitation to the synchronous condenser, and it can also help in providing reactive power and boost the voltage. It has also the feature, it can absorb the reactive power. So if let's say it can do both the jobs of it can also mimic the capacitor, it can also mimic the reactor. So it can absorb the reactive power when you have to reduce the voltage, it can inject the reactive power when you have to boost the voltage. Another advantage of synchronous condenser is that it helps in increasing the short circuit capacity of the system. So obviously the system can sustain higher fault currents, and also it can help in stabilizing the system by supporting in power swing. So swing we have not discussed in the course, but I hope you have heard this term power swing. So it also disturbs the system, and this generally happens when heavy load is being cut out or started, so power starts swinging across the system. So it can also lead to instability. Right, so this is about the synchronous condenser. Now let me just explain you static VAR compensators. It is also, you can also say it is just the capacitors and reactors. You can also there are few types of SVCs, and you can also say it's a static because there is no moving part here, and basically you can aggregate multiple SVCs to basically provide different voltage range at the output terminal. So basically few types of SVCs are saturated reactors, thyristor controlled reactors, thyristor switched capacitors, thyristor controlled transformer, even line commutated converters. So these are the few types of SVCs, but I'm not going to go into all these things. I'll just quickly explain you a basic phenomena of SVC, how the switched static VAR compensators generally work. So I'll just give you a quick understanding of that. So basically it is ideal SVS or SVC. You can say that there is a HVAC system or HVAC bus is connected, high voltage AC bus, and let's say you have an inductor which is a switched inductor. You can vary the inductor, let's say and that is connected with in parallel with a switched capacitor, where capacitor also you can vary. So here you can say that initially, let's say at the HVAC bus, the voltage is at V0. So wherever is the current IS is the current which is either it can be drawn or injected by the capacitor or inductor. So let's say if it is drawn by the inductor, then it is in the lagging. If it is drawn by the capacitor, it is in the leading. Wherever is the current, the voltage will always remain flat. It will always remain at the nominal value. So that is the ideal SVC systems. But realistically what happens is let's say if I keep the inductor at maximum inductance value, then let's say I disconnect the system. So first let us see if, let's say, only the inductor is connected. So, and let's say max inductor is set, we set the value of inductor at the maximum value. Then let's say there will be, as soon as the current increases in the inductor, the voltage changes, and as soon as you change the inductor value, there will be some change in slope, and then you can, further as the current increases, you can further increase the voltage based on this. And it is on the right hand side, so you can see it will be lagging. And let's say if the fixed capacitor is there, then what will happen, because it's a fixed capacitor, it will, as the capacitor current increases, the voltage is increasing at the left hand side, and this is in the leading form. So basically if you add both this up, you will get the final this SVC systems, where you will see that there will be a capacitive value and you can change the inductor values, and then you can get the different voltage values as per the current. So this is the way you can actually control the system voltage. Either you can keep it at the leading or lagging, depending on the situation, depending on the connection point, what is the value at voltage at this point, right? So I hope this is clear. This is I just gave you a brief introduction what exactly is happening and how this SVC system is working, so you can easily control and you can get the features of both injected reactive power as well as absorbing reactive power. So now let's see from the power system point of view. Let's say if we convert the power system network in the Thevenin equivalent form, so you will get ETH, which will be Thevenin voltage and also a Thevenin reactance. So if let's say if we convert this HVAC system into a Thevenin equivalent form, so you will get a Thevenin voltage and a Thevenin impedance, and then let's say you connect a variable reactive load to this terminal. So what will happen is, let's say if this load is basically on the inductive side, so the voltage will reduce, the voltage at this V terminal from the ETH, and if let's say if the reactive load is capacitive, then the voltage will increase at the V terminal, right? So this is the slope which you are going to see here. Now let's say if you want to improve the voltage, so you can shift this line vertically up and down by changing the ETH. So if you let's say change the ETH, or let's say you change the generator terminals set point, voltage set point, then you can vertically move this line up and down. And if you change the series reactors, shunt reactors, transformer taps, these are basically the network parameters, then you can actually rotate this XTH in both different directions. So if let's say you are increasing XTH, it will rotate in the clockwise. If you are decreasing the XTH, it will rotate in the anti-clockwise direction. So this is the power system characteristics. Now let's merge both power systems and SVC and see how actually it operates. So let me just show you that. Any queries before we proceed? So this is just a story, you can just listen and try to understand this, and if you have any queries, let me know. So let's say if I just merge the SVC and power system characteristics, so this diagram, just bear with me for a while. So let's say you see here a point where V0 voltage is there, right? So let's assume the system was operating at V0 and everything is fine, and let's assume the load we have switched off. So the load which was connected, we have switched off the load. So as soon as the load reduces, generally what happens, the voltage increases, and let's assume the voltage increases and reaches to V1 point, right? But now let's say V1 is assumed that the V1 is a very high voltage and it is crossing the maximum voltage limit. So what, and then obviously this is a problem that we do not want this voltage to cross the maximum limit. So what we can do is if we have a SVS system which is installed nearby that load, so what you can do, you can, if you switch on that load, that SVS system, instead of V1, this voltage will move to this point, B point, where the voltage will be V3, and that means this SVS system will be giving a I3 current, which will be an inductive current, and eventually it will reduce the voltage increase because of the load loss. So this is the way you can control the SVS, and also you can control the voltage in the power system. We can take the reverse example. Let's say the load has been added on the system. So let's say initially voltage was V naught and you have added the voltage, added the load. So as soon as you add the load, let's assume the voltage will drop at V2. But obviously, if let's assume V2 is the load which is a very high value of load, then what happens, you can install a SVS there, and instead of V2, the voltage will actually go to this C point where voltage will be V4, and I4 capacitive current will be injected by this SVS system to ensure that the voltage does not drop further. So this is the way you can actually see that SVS systems are supporting. So one is synchronous condenser, where you get both the features of reactive and active power. The same is with the SVS, that you get both the active and reactive power features. Here we say it is SVS because it's a static, and it is very easy to operate and easy to control, and it's a very small setup compared to the synchronous condenser. So that's why most of the people prefer this devices. Obviously these days FACTS devices are there which are even more easier to control. I'm not going to that because it is all thyristor based. I'm not going to that, but if you are interested, you can read more about that in the books, specifically the book which I have mentioned, which is Prabha Kundur. It is a very good explanation of those topics are given in that book. Any queries, or is it fine? Okay, so let me go ahead from here. So I'm just giving you one example, that let's say you have a situation here that there are one reactor, switched reactor, and there is one reactor plus capacitor in series connected in parallel with the switched reactor, and then you have a switch and a capacitor again connected with parallel to the system, and then a capacitor again with a switch it is connected. So let's say if all these switches are open, and we are just talking about the system 1, this is the system 1, then you can only, because there is more reactor here, so you can only get less of active capacitive feature, more of an inductive feature, and after a while the voltage will go beyond its limit. And if you can obviously switch on more capacitors to bring the features of more capacitive and less reactive. So you can have this setup, and this is a very customized setup. So basically it is very easy to expand, and you can install more reactor or capacitor to get both features of capacitive and inductive. So it depends on the place where you are installing this, and if that place requires more inductors, you install more inductor parallel to this. If you require more reactor capacitors, you install more capacitors parallel to it, and you can get the same features similar to what we have just discussed. Right? Any queries? So basically, how does this work? Complete reactive power thing. How does it work? So basically, as I have told you before, we actually run AC OPF. That is, again, there is a catch here that we do not run AC OPF directly. We run DC OPF, but okay, just for simplicity, let us go with the AC OPF thing. That we run AC OPF. From this AC OPF, we get the values of voltages and Q, and this voltage is actually given, and we run a power flow, or simply just let's say if we get the value of voltages, you ensure that the voltages at the shunt reactors or shunt capacitors or SPCs this voltage has maintained. So basically you also get the information of Q from ACOPF. If you take the SVCs as variable, then you can also get the value of Q for these SVCs, and based on that you can decide how much capacitors or inductors you have to switch on or switch off to maintain this voltage. So this information you can get from OPF, or what you can do is what we do practically is we run a DC OPF or economic dispatch which does not have reactive power related expressions or voltage expressions. We just run simple the DC model, and from this we fix the P values and run a power flow, and based on some regulatory guidelines we ensure that the voltages at the generator terminals are fixed, and then we adjust the switches or Q of these switches of SVCs so that we can bring the voltages within limit if it is violating. If everything is fine, then we go ahead with that setup, or we can switch on, or we can change the transformer tap value, we can change the SVC settings to bring the voltage within the particular limit or within the specified limit. So this is the way we generally control the reactive power in using these passive and active compensation devices. Right, so I hope the concepts are clear to everyone now. Now, any queries? Okay, if no queries, then let me just quickly go ahead and tell you we missed out on one thing, which is we saw the reactive power control for SVCs. Now there is another feature which is very important. You can obviously control the reactive power or the voltage by the AVRs. AVRs we have missed. So AVR is basically controlled by these excitation systems which are in place in the synchronous generators. So all the synchronous generators have the excitation system which actually control the voltage at the generator terminal. So the basic so I hope the previous things are you are able to understand that, but this excitation system we are going to see this for a while, for 10-15 minutes, and then with this we'll close the session. If you have any queries, you can let me know. Okay, for the excitation system, the basic function of excitation system, it provides the DC current, direct current, to the synchronous machine field winding so that it injects the reactive power or absorbs reactive power based on whatever is the situation. And also it ensures that it also works on protective functions. So protective function means it actually needs to ensure that the field voltage, field current, and also the terminal voltage of the generator, this is all working and it is giving a satisfactory performance. So basically related to the voltage of the synchronous generator, what all things we have to ensure is taken care by the excitation systems related to the voltage. And these control functions, so control of protective function, these functions actually focus on voltage and reactive power, and also it also focuses on enhancing the system stability. And the protective functions actually ensures that the generator is operating within its capability limits, its excitation systems are within limits, and also the other equipments which are there or in the power plant all the equipments are operating within their limits. It's not violating. So these are also ensured in the excitation system. This is all in terms of voltage and reactive power. Right, active power we have already seen. Now we are only focusing on reactive power and voltage. Right, so basically just to tell you, from the excitation system there are two requirements. One is from the generator side and one is from the power system side. So let me just quickly tell you from the excitation system what does generator expects from the excitation system, or generator or power plant owner. So from the generator point of view, the basic requirement for excitation system is to control or adjust the field current such that the terminal voltages are within the capability or within the capability range of the generator. So basic idea is to ensure that the voltages are basically, field current is adjusted for the synchronous generator such that the voltage remains within the capability limit of the generator. Obviously, because it is all current and then the voltage is generated, so basically you also need to ensure that the temperature of all the components are within limits. You need to also ensure that the components failures can happen, and you have to ensure that those things do not happen. You also need to ensure that the emergency overrating of the some of the components can be done, and that also needs to be ensured. So basically, generally, if we are talking about temperature, so the idea is, let's say if you are overloading some of the components, generally it can be overloaded for 15 to 60 seconds so that basically the temperature is increased because you are increasing the heat, that is I square RT. So you can just go for 15 to 60 seconds so that you can bring the voltage or to satisfy the voltage, and then you can bring the current back to the within limit so that the temperature is within limit. So basically you can violate for small duration and then again bring the voltage back to the capability limits of the generator. Also, you can see that the exciter rating is 2 to 3.5 kilowatt per MVA of the generator rating. So let's say you imagine if, let's say, it's 1000 MVA generator, so you can imagine for 1000 MVA generator 200 kilowatt will be used for excitation system. So you know that's why generally the coal based or the thermal based power plants have a very less efficiency. Specifically, coal based power plants are having efficiency around less than even 60%. So somewhere around 50 to 60% is the efficiency of that power plant. So you can imagine how less efficient it is because of these. A lot of factors are there, but this excitation system, you can imagine how much power they require for a particular rating of the generator. And these voltage changes or the excitation system should be able to respond to the transient disturbances. Transient means a very small disturbance. If it is happening in the network, it should be able to respond to those disturbances as well, right? And also the generator capabilities, this is just the capability curve which we have discussed before. It is limited by the rotor insulation failure, which can happen because of high field voltage. So if you have increased the voltage to a very high value, then the rotor insulation failure risk is there, which you have to check that you do not go beyond a particular value. If you have high field current, then heating will be there, which you again need to reduce the temperature current so that the temperature can be brought within limits. And also, if let's say high armature current is there, then stator will start heating up. If it is under excited operation is happening, under excited means you are absorbing reactive power, then core starts getting heated up, and if more flux is being transferred from rotor to stator, then again heating will take place. So these are the few limiting factors which you need to ensure to ensure that the generator remains within the capability curve. right? And lastly, I have already told you that the thermal limit is actually a time dependent phenomena, and you can overload the system for few seconds to satisfy the voltage. Let's say if in case of emergency you can overload the generator for few seconds, and you will get some time margin to switch on some other devices and bring that the generator back to the nominal value. Right, so these are the excitation system requirements for from the generator's point of view. Now, if let's say if we see the same excitation system requirements from the power system point of view, what will be those features? So from the power system point of view, the power system wants that the voltage should be effectively controlled, and it should enhance the system stability, and also the voltage should be means it should respond to the system changes at a very high pace. Basically, it should rapidly respond to the voltage changes so that the stability of the system is not lost. So basically, small signal stability, to be specific, is exactly getting affected because of if the voltage is not being responded rapidly. So that is what you have a power system. Means this is the excitation system requirements from the power system point of view, and to satisfy these requirements satisfactorily, excitation system should meet a specified response criteria. So basically it should behave in a proper manner. So there is a control system which actually ensures that the excitation system behave in a proper manner. It also has some limiting and protective functions. So as we have seen that we should not violate the rotor heating limit and rotor current limit so that it damages the generator. So that also needs to be ensured, and this requirement is basically should be such that we should get the operating flexibility from these excitation system. And also we should get the desired reliability and availability for this desired reliability and availability should be there of reactive power, and specifically when there is a fault because whenever internal fault is taking place, then you get then the rotor heating happens more, so you also needs to ensure that, and isolation capability should also be there. Isolation capability means, let's say a network is power system, in power system, let's say if there are two areas and if they are getting disconnected, then obviously they are not getting support from the neighboring areas, what we have seen in the example also. In that situation, there should be, the generator should be able to have sufficient reactive power capability available with them so that they can provide voltage even in isolation or even in islanded mode of operation. Right, so I'll just stop here because I have because it's lot of material I have given in just one day. So I hope you got the idea of how the reactive power control is happening through the passive devices like shunt capacitors, shunt reactors, shunt series capacitors. You also have transformer taps, you also have SVCs, you also have excitation systems. We will be seeing more quick detail about excitation system in the next class, but I hope you got the idea of the complete reactive power control. There's very few remaining things which are there.